Hey everyone, welcome back to the 5th episode of the xHCI driver development series. In the last episode, we finished setting up the command ring and briefly mentioned the event ring data structure. And as much as I can't wait to get into actually setting up the event ring, allowing us to send real commands to the controller, we first have to cover the topic of runtime registers, which is what this episode will be focused on. The runtime registers will directly lead us into the event ring, and in the meantime will allow us to enable and manage xHCI interrupts that our operating system can receive and handle. So without further ado, let's jump right into it. The xHCI controller exposes what's called an interrupter, or more formally an interrupter register set. The first two 4-byte registers, IMAN and IMOD, are the interrupt management and moderation registers that allow you to control the fine-grained timing of scheduled USB traffic, as well as enable xHCI interrupt or check if one is pending. The next three registers are all related to the event ring management, and we're going to go over them in the next video when we actually allocate and set up the event ring. You can think of an interrupter as a personal mailbox for events. The controller fills the mailbox whenever some operation is completed, and the operating system can check it when notified. The notifications come in a form of system interrupts, and the OS can check for events using the event ring, which similar to the command ring in the previous episode containing CRBs, but this time with event completion CRBs rather than commands. In this tutorial series, we will only be using one interrupter, interrupter 0, but in a more sophisticated system, you could have many such interrupters set up. Let's say our system has 8 CPU cores. And as you may know, most modern PCI devices use either MSI or MSIX based interrupts. In xHCI, each interrupter maps one-to-one to each MSIX vector. Subsequently, using the PCI memory space, you can set up a table of these MSIX vector entries to route the interrupts to different CPU cores. So if you have a complex SMP system, you could set up multiple xHCI interrupters with different timing configurations and settings and route them to different cores to perform some advanced load balancing, for example. If this feels too complicated right now, don't worry at all, because again, we will only be using one interrupter set, and it's actually really simple to set up. So let's jump into the code and get right into it. Let's start by opening our xHCI regs.h file and add a couple structs to it. First, let's define a register set called xHCI interrupter registers, which will grant us access to registers within an individual interrupter. The first register in here is an interrupt management register, which is responsible for enabling or disabling interrupts as well as indicating whether an interrupt is currently pending. Next, we have an interrupter moderation register, which you can use to control and throttle incoming interrupt frequency. Third register is the event ring segment table size, which we'll get to in the next video. Then the next 32 bits are simply reserved. The next register is now 8 bytes long and holds the base address of the event ring segment table. And finally, we have an 8 byte long register again for the event ring DQ pointer. And for the convenience sake, I will also break it down into bits using a union here. Again, don't worry about any of the event ring related registers now, since we'll get to each of them in the next video when we actually set up the event ring. Now that we can describe what a single interrupter register set looks like, let's define a struct for the xHCI runtime registers. The first register is a microframe index, which can give us finer grained control over scheduling and timing the USB traffic, but we will not be using it in this series. It is then followed by 28 bytes, which are all reserved. And finally, we have a huge set of these interrupter register sets that we defined earlier, 1024 of them to be precise, and each one maps directly one-to-one to the MSI or MSIX vector table entries. Now I just want to mention again that in this tutorial series we will only be using the first interrupter register set, with only one event ring, so we can ignore the other 1023 interrupter sets. Great! Let's now go back into our main xHCI.h file and add the runtime register set as a private member of our driver class. Similar to how we configured the operational registers before, we now need to create a function to configure the runtime registers before we start the controller. And going into the xHCI.cpp file, let's call it after we set up the operational registers in our init function. Great, so now let's go down to the bottom of our file and actually define it. So the first thing we're going to do is get our first and primary interrupter register set. Just a reminder, make sure to mark it as volatile to prevent compiler optimizations from messing with memory accesses to these registers. Now we need to enable the interrupts, and we can do that by first reading the interrupt management, the IMAN register, into a local variable, then setting the interrupt enable bit to 1, and writing the new value back into the IMAN register. The next thing we would typically do here is allocate and set up the event ring, but that will be the focus of the next episode, so for now let's just leave a to-do comment here. Finally, the last thing we have to do here is clear any prior pending interrupts. And since we will need to be able to do this again later on during interrupt completion, let's abstract it into its own function and call it acknowledge error queue. And to do things the right way and make it scalable in the future, let's also make it take in the interrupter index as a parameter. And going back to the CPP file, let's define it below, and we'll call it here in our primary interrupter at index 0. Now as for implementation, we first need to get the appropriate interrupter register set based on the provided index. Then we have to do a similar read, update, write-back routine with the IMAN register like we did before, but this time we have to write a 1 into the interrupt pending bit in order for it to clear any pending interrupts. Now according to the spec, we also have to do one more thing here. We have to clear the event interrupt bit in the USB status register in the operational register set. But in order to avoid race conditions, we have to do it before we clear any other interrupt pending bits in the runtime registers. Now, if you've been paying attention, you might be asking a question at this point. We keep using the runtime regs variable, but we never actually initialized it. And you're absolutely right. So let's go do that now. Back when we parsed the capability registers, we initialized the operational register base address using the cap length register. And similarly, for the runtime registers, we have to use the RTS off register in the capability register set, and use it as an offset from the xHCI base address. And that is it for today. I won't show compiling and running the project now since we haven't added anything worth printing yet, but we definitely will in the next episode when we focus on setting up the event ring. Once the event ring is set up and we've started the controller, we will be able to actually start communicating with it and send real commands, which is going to be super cool. We're literally so close to finishing setting up the controller and starting it again, so congratulations on making it this far. You should really be proud of yourself. I want to thank you again all for watching, and hope to see you in the next one.